Okay, here is your simple harmonic motion lab. There's the first spring. I've got it at 24.2 centimeters. And then 28.4 with 10 grams on it. $20 grams. I'm at 32.7. 30 grams. I'm at 37. 40 grams. Looks like 41.2. 50 grams. 45.5. Okay. Move back a little bit. Okay, so let's do spring number 2. Spring number 2. There we go. At rest, we're at 25.9. Oh, I better do it 20 at a time. 20 grams. 26.7. 40 grams. 28.2. 60 grams. 29.8. 80 grams. 31.3. And 100 grams. 32.9. Alrighty, so there's the second spring. Now I'm going to put the 2 springs like this, and I'm going to choose 40 grams, I think. I'm going to put 40 grams on the end here and set it into simple harmonic motion. There it is. All right, that should be enough to determine the period and the frequency. Now we need to set it up in parallel. So that was your series, if you remember from the Hooke's Law lab. Let's see if we can bring this up to where it's even. All right. I'm going to put these 2 together like this with 50 grams on it. Oh, I think I need more. I'm going to do 100 grams. There it is. Oops. Let's do 200 grams. Okay. There it is. Good. parallel. Those are in parallel. There you go, and you can do. Should be able to calculate the frequency and the period from that. All right. Now we want to take a look at, the next thing we're going to look at is making a simple pendulum. And here's our simple pendulum. The length of the pendulum. We'll measure that. I'll hold this right up here. All right, so the top is at 10 centimeters. And there's the bottom down there. I'm going to say center of mass at 74.5 centimeters, and the top at 10 centimeters. And that's, so that will give you L. I have a 50-gram mass on there. And so set it into simple harmonic motion. There we go. And measure its period. All right. All right, so that should do for the first part. For the second part, we need to change the angle and measure frequency and period at different angles. So I'm going to go as 30 degrees, and you can measure the frequency there. I think before it was around 10 degrees. There we go. So you should be able to measure that. And you can't let it go for very long because it's going to start to lose amplitude pretty quick. And I'm going to go up to 60. Which is right about, trying to get to 60. Right there. Okay. So there's a 60. Okay, and you can't use many more than that because it's going to be so low. And then if I can get to 70, let me see if I can get to 70. 70 would be up there. Oops. No good. All right. Let's see if we can do this. We'll disassemble this part. All right. Get rid of these. All done with those. And then let's see if we can get this up to 70. We'll go this way. We'll go to 70 right there. Okay. Oops. Let's try again. So I hit my spring there on the other side. So 70. I'll be right about there. Oops. Right about there, 70. That's good. Once again, it quickly, the amplitude quickly goes down. So you got to calculate this period right away. Okay, so that should give you some data to put into a graph to see if the small angle approximation breaks down. The next thing is the physical pendulum. And for that, I am going to use the ring that we used in the moment of inertia lab. Okay, so here's the ring. That might not work. Let's try something else. Let's just do what I did in class, which is to use a meter stick. Okay. So here's the meter stick. And I'm going to attach it here. There we go. And then we'll measure its period. So that's better right there. Okay. And hanging it from the end, you can see there that it's a little bit away. I'm not sure if it's actually moving. I'm going to have to do a little parallel axis theorem here because I think this whole thing is moving with it. You can ignore the mass of the paper clip, but I think you've got to do the parallel axis theorem because I'm going to add 4 centimeters to the length of the ruler. All right? Or the length of my pendulum anyway, not the ruler. But the pendulum itself will be 4 centimeters longer. So here it is. Just set it into motion and you should be able to easily measure its period from seeing it move back and forth. Okay. Let's try it again and you can measure again. There we go. That's our physical pendulum. And at the end, we'll get a mass for the ruler. You need a mass for the ruler. All right, meter stick. Okay. All righty. And the last part is the torsional oscillator, which we are going to use right here. We have a torsional oscillator here. We have a 1 kilogram mass on the end of a spring. The mass has a diameter, looks like 5.3 centimeters. Let me just measure that again. More like 5 centimeters. 5 centimeters is its diameter, and it's 1 kilogram mass. I'm going to tape everything together here so we don't get any slop. We don't want this part in here to be twisting at all. It needs to be attached to the spring very easily. You can see if I turn it this way, The hook and the ring don't interact in the way that I like. So I'm going to make this really tight here. Similarly up top here, I got to prevent that from wiggling. So I'm going to use another piece of tape to stop that from wiggling from happening, which should make my results more accurate. That looks like that's rotating together now, which is better. And before we measure the period, we need to try to find kappa, which is the rotational constant of my torsional oscillator. So again, I'm going to do exactly what Cavendish did, which is to need to calibrate my torsional oscillator. I'm going to get a spring scale. I can find one. There'll be some in here. There we go. Good. I got a 5 Newton scale, and I'm going to attach a pencil or something to this that I can twist it and measure the force, and then thus, if I know the distance away from the axis of rotation, I can calculate the torque that it takes to twist this. All right. Yeah, there's a plain pencil. And I'm going to cut a notch in it so that the hook on my spring scale goes right into the notch. And that will give me an accurate measure of the R and R cross F. So I will be able to keep the pencil right at or the meter measurer for the spring scale right into that place right there. Okay. So let me get this attached on here again. I don't want this to wiggle at all. I want to be able to make sure that when I twist it, it's twisting everything. All right, so there we go. All right. So find out where its equilibrium position is right there. And then I am going to twist it around twice. There's 1 rotation. And there's 2 rotations. And let me measure this force. There is the force. I'm getting like 0.4 newtons. 0.4 newtons. Okay. There we go. Okay. So now 0.4 newtons, and the distance between this axis of the spring and where I measured the force, I get 9.7 centimeters. Okay, so 9.7 centimeters away from the axis. Okay, so there's your data in trying to calculate kappa. And now we're going to set it in motion and see what the frequency is after I get this pencil off here. Okay. And this might be a little harder to see. We'll get up a little closer here so you can see it as it spins. There it goes, and you should be able to calculate the period by timing it. I would say take a good 5 oscillations and it should do it. Not the up and down, it's the twisting. She's twisting pretty good there. I don't see any movement between the mass and the spring. It's really holding its own. They're pretty good there. And again, the shape of the mass is going to be a cylinder, so that should be easy to figure out its moment of inertia given its radius and mass. Okay. And again, the period should be independent of the amplitude of the oscillation. So no matter how small the oscillations get, they should still have the same period. We did not make a small angle approximation here. Alrighty. And that should do it. Okay, the only thing we forgot was the mass of the ruler, which we're going to get right now. And if we put the ruler right on the scale, first make sure the scale is zeroed correctly. I'm going to go this way a little bit. That's better. There we go. Okay. Put this on here. It should be around 75 grams if I remember right. Of course, these rulers are all different. A little bit more. There it is. I get to 71.8 grams. 71.8 grams. Yep. And I think that's the only mass we need because that was our physical pendulum, yes.